Ionization energy is the energy required to remove the outermost electron from 1 mole of atoms in the gaseous state. Is the energy required to move the second electron from 1 mole of the 1 plus ions in the gaseous state, and the third ionization energy is then the energy required to remove 1 electron from a 2 plus ion in the gaseous state. As you can see, as they go along with successive ionization energies, the energy required to remove that outermost electron increases. Obviously, this is not an incremental change, but there are big jumps. So in this example, you can see a jump between the third and the fourth ionization energy. Okay, that tells you that you're now moving into a new shell, so the element is in the third group. Okay, so as we go across a period, a few things to notice. So, for example, in period 3, going from sodium to chlorine and then on into argon, that the atomic radius is decreasing as we go across the group. Okay, so the outer electron is being more attracted to that more positive nucleus because the amount of ions as we go along. So if we compare the ionization energy of sodium to that of chlorine, the ionization energy of chlorine is going to be much higher because it takes much more energy to pull 1 electron away from 1 mole of gaseous atoms. Okay, whereas know that from the atomic number, so sodium with an atomic number of 11, chlorine with an atomic number of 17, so the ionization energy increases as you go across the period. If we look at the electron configurations of the elements using SPD notation, we can see that sodium, for example, has an electronic configuration of 1 3s electron in its outer shell. Magnesium has a full S shell, whereas aluminium has an extra electron in a 3p subshell. So there's extra shielding from that 3s orbital and therefore a lower ionization energy, whereas silicon has 2 electrons in the p shell, so it's going to have a higher ionization energy than aluminium. Sulfur again has one paired set of electrons in its p orbital, so therefore there's electron repulsion there, and it's going to be slightly lower than phosphorus. And again, chlorine and argon are going to be an increased level of ionization energy because of the increased nuclear charge. We can measure the atomic radius in a metallic bond as half the distance between the 2 nuclei. So, for example, in this magnesium, it's half the distance between the atoms, the nuclei of the adjacent magnesium atoms, whereas in a covalent molecule such as chlorine, it's half the distance of the bond length. Okay, so the atomic radius is half the distance of the bond length between the chlorine atoms. So as we go across a period, we see that the atomic and it's decreasing because of the increased nuclear charge that we have, and that accompanied with no increase in shielding means that we have a decreased atomic radius. So we can show this graphically in a graph, and you see an exponential decay of the distance of atomic radius.